Peace, mercy, and blessings of Allah be upon you. Now we want to see together how you can create a transformer vector group. In fact, to study something like this, we first need to talk about three things. Number one, what does a transformer vector group mean? Number two, why do I have transformer vector groups? Number three, how is the transformer actually wound to achieve a specific vector group? Very nice. The first thing we have is the transformer vector group, or the directional group of transformers. Simply put, you have the three-phase windings of the transformer that can be connected in different ways. And based on this connection method, the transformer vector group is determined. Let's take an example of this written on a transformer on its nameplate. DYN3. So, what does this mean? The D, which is a capital letter, refers to the primary or high voltage winding connection, which is connected in a delta configuration. The E in are small letters, and this means that the Y refers to the secondary or low voltage winding connection, which is in a star configuration. The N means that this star connection has a neutral, and this neutral is connected with the ground. As for the last number, which is 3, it is an indicator. This number is multiplied by an angle of 30 degrees, meaning 3 times 30 equals 90 degrees. This means that the line current on the star side lags the line current on the delta side by 90 degrees. The second thing we have, in fact, is that I need the different vector groups in transformers for several reasons. Number one, they help me eliminate what is being drawn through. Or, number two, they help provide a closed path for the narrative and prevent its appearance on. And I can achieve this when the transformer is connected in a form. And also, it can provide a path for the fault current with the ground, and this is in case I can achieve it when I connect the transformer in a star form, and this star has a neutral, and this neutral is grounded. So why is it necessary to determine the vector group of transformers? In fact, this helps me in two things. One of them during the calculation of the final setting for the transformer differential protection. Another thing is when connecting two or more transformers in parallel, and this is to avoid the large circulating current that occurs between the transformers. At this point we know, or in most stations, when you have a switchgear consisting of 3 sections, you usually have 3 incomers, and the switchgear operates on a 4 out of 5 scheme, so you usually have 2 transformers connected in parallel. In this case, the transformer vector group must be determined. The important question here is whether both should have the same vector group. The reality in stations is that, of course, both should have the same vector group, if they differ in the vector group. Here, I will provide you with a link to a video, and I would like to thank the EEB page and engineer Hani Kamel, who explained to us that you can change the cable connections as they enter the bus bar to achieve compatibility between the transformers if they have different vector groups. This is a very important point, and as I mentioned, I will leave the link in the video description. The third thing we have is the transformer winding connection, or the method of connecting the external terminals of the transformer to obtain a specific vector group. Let's take an example of this with DYN3. Alright, now I will get the transformer core, which consists of 3 limbs, and on each limb I will connect a phase. Here, a red phase, a yellow phase, and a blue phase. Each phase consists of 2 windings, one for the high voltage side and one for the low voltage side. For the high voltage side windings, their terminals will be represented by capital letters, and for the low voltage side windings, their terminals will be represented by small letters. Very nice. Another thing we will notice here is that the terminals of the high voltage side A1, B1, C1 will correspond to the high voltage side terminals A1, B1, C1. As for A2, B2, C2 and A2, B2, C2, meaning from the high voltage side and the high voltage side, they will be on the outer terminals. Okay, now if I asked you to draw the phasor diagram for the currents of the high voltage side and the low voltage side in a very simple way, you would now draw IA, IB and ICA on the high voltage side such that there is a 120-degree shift between them. And similarly for the low voltage side. Okay, now you asked me for a directional group called dyn3. And this means that the line current in the star side lags the line current in the delta side by 3x30, meaning 90 degrees. So here I come to draw the 90 degrees in the direction of the lag and draw my new physio diagram for the planes IA, IB, IC. Any shower, IP shower, AC shower. Then I carefully and precisely draw the windings for my new phasor diagram, and I go to the phasor diagram for the delta and draw the shape of the delta connection. Very good. I now see each winding here in the star side. Who distributes it here? For example, if you see that you have a red phasor winding positioned horizontally, this winding will be distributed, and you have a yellow phasor winding that will distribute this winding, and a blue phasor winding that will distribute this winding. Therefore, I will color the windings so that this parallels this, and this is also the red phasor winding. And this is the winding for the yellow phasor, and this is the winding for the blue phasor. All right, then I will come here to the star connection to form the neutral point. You have each winding with two terminals, A1, A2, B1, B2, C1, C2. So where will you form the neutral point? I will form it on the side of A1 with B1 with C1. So my terminals will be like this. A1, B1, and C1 are facing each other here to form the neutral point, and A2, B2, and C2 are the external terminals. Great, so how will my terminals be here? Let's focus here, and notice that this coil is parallel to this coil. So we drew this one as if it goes from A1 to A2 in this direction. I will also place it here to ensure it follows the same directionality, from A1 to A2, and similarly from B1 to B2, and from C1 to C2. Then I will find that these are the terminals that have appeared. Therefore, when I connect the terminals, I will connect A1 with B1 with C1, to 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 connect A1 with B1 with C1 to con a phase and on a phase cable. As we can see, and regarding the delta, what will I do? As we can see, we will go 11. I will notice here that P1 is connected with C2, and C1 is connected with A2, and A1 is connected with B2. The first thing I will connect is P1 connected with C2, and these two go to U. The first thing is the connection with STU. And where do these two go? They go to the red phase, the hall. Then we will find that C1 with A2 are the ones who will go to the yellow phase. We will connect C1 with A2 and send them to the yellow phase, which is V. Then we will find A1 with B2 will go to the blue phase. We will connect A1 with B2 and send them to the phase. Therefore, if we assume that I have an external voltage on the red phase towards the star side, the current, for example, will be drawn here going towards the fault, moving from A1 to A2. In this case, the current will be drawn from the red phase towards the delta side, from the red phase winding in the transformer, so that it will be in the direction from A2 to A1. Nice. Nice. Okay, for this current to be drawn from the external circuit, from the cables outside, I will find that the terminals of the red phase winding are connected to whom? Yes, they are connected to the yellow phase, which comes in here, enters the winding, and exits here from which phase? From the blue phase, meaning it came from yellow and exited from the blue phase. It didn't actually draw current from the red phase cable, but here, just to be clear, on this point, the current, as it is drawn from the red phase in the star, is drawn from the red phase in the delta as a winding, but as external terminals from the transformer due to this vector group. It is drawn here from the yellow and blue phases. Pay attention to this information. It will be very useful when we later discuss vector group compensation in numerical relays, because I will notice here that this current is matched by a current in two completely different phases that have nothing to do with the red phase. So how will the relay handle this and process it internally? With this, we managed to wind our transformer in a DY11 configuration, which is excellent. This concludes our lecture.